Sarah Lancaster, an Extension Weed Management Specialist at Kansas State University. This webinar is going to discuss interactions that occur between herbicides and soils. So we're talking primarily in this case about residual herbicides. Residual herbicides are a critical component of any weed management plan, but they've become even more important as we think about how to best manage and prevent the development of herbicide-resistant weeds. So we often use these products at planting, but there's an increased emphasis on the role of these products in post-emergent herbicide applications. So we know that residual herbicides have a certain length of activity, and we're going to discuss later in this webinar about some of the things that control or regulate that length of activity. But we also know that the crop canopy develops over time, and sometimes that residual herbicide wears out before the crop canopy is dense enough to provide enough shade to prevent weed emergence. So we often use post-emergent herbicides about the time that the residual herbicides start to break or start to lose their activity. If we don't include a residual herbicide with this post-emergence application, we still have the potential for weeds to emerge until the closure of that crop canopy. So thinking about the development of your crop and the characteristics of your residual herbicide and your environment can help you figure out how to best utilize residual herbicides throughout the growing season. So again, just to illustrate here that when we apply that residual herbicide with our post-emergent herbicide application, we extend the activity, the length of activity of that residual herbicide in the soil and can prevent weed emergence for a longer period in the crop. When we apply those residual herbicides, there are a variety of things that can happen. Some of them we're going to focus on in more detail in this webinar. One that we're not going to touch on much is the idea of leaching. And so leaching is just the process that occurs when that herbicide dissolves in the water that's in the soil and then moves out of really the active zone for that soil profile. So it's going to be washed away and leave the site. Leaching is generally considered to be a negative thing, right? This is why a lot of our herbicide labels have restrictions in terms of the soil types on which in terms of the soil series on which they can be used, and concerns about groundwater issues. A second possibility that can occur when a residual herbicide is applied is plant uptake. And this is the goal, right? We're putting these herbicides in the soil so that either the germinating seeds, which I tried to kind of cartoon out here as these green circles with the little radicals emerging, or as growing plants. So the process of transpiration is pulling water through the plant, which is causing the soil solution that has herbicide dissolved in it to be taken up into the plant. Okay, so that is our intended goal. Different herbicides, even though they're all considered residual herbicides, are absorbed by plants differently. And this is one of the things that helps to determine how that herbicide is going to work and what weeds it's going to kill. So we've got in this chart here different herbicide modes of action, the site of action groups associated with that, some examples of some products, and then how those various herbicides are taken up by weeds and other plants. So the first group here would be the seedling root growth inhibitors, group 3. So an example of that would be Prowl. This is a product, or these are products that are taken up by the emerging shoots and roots as they first come out of the seed. So in this case, we're not likely to see the affected plants emerge above the surface of the soil. The second row of this table here, we've got our photosynthesis inhibitors. You might hear them referred to as group 5. So that would be products like atrazine, metribuzin, and some others. These are taken up by the roots. So these products, even though they stay present in the soil, the plants actually need to be growing and taking that herbicide into the roots. So this is why these herbicides will also control plants that are already emerged. So they're residual herbicides with some post-emergence activity. Group 14, the cell membrane disruptors, or PPO inhibitors. These are things like Valor or Spartan. These are also taken up by the roots. Group 15, this is a very common herbicide that we look at in terms of controlling grasses and small-seeded broadleaf weeds pre-emergence. These herbicides are taken up by the emerging shoots and roots. So again, the activity is happening before that seedling comes to the surface of the soil. The last group here on this list would be the bleachers or the pigment inhibitors, group 27. So things like Balance, Callisto, maybe Impact. These actually can be taken up by seeds, roots, and shoots. So the second or the third thing that we need to look at here in terms of what happens to herbicides after they're applied to the soil is a process called sorption. So in my little cartoon here, we've got different soil particles, sand, silt, clay, and some organic matter. The two components of the soil that are most important for sorption would be the clay fraction and the organic matter fraction. So here's a kind of blown up cartoon of what might happen in the soil that facilitates sorption. So a couple of things to look at here. One would be characteristics of the soil. So we know that most soils have a net negative charge. Hopefully you remember, if you had a soils class at some point, you remember that. They also have different minerals that can be present on the surface of those clay particles. And then organic matter is mixed in and interacting with all of this, okay? So the interactions between the specific herbicide molecule and the specific part of the soil is what drives these interactions and the extent of sorption that occurs. And so this is one of the reasons why we see different herbicide behaviors on different soil textures, different soil organic matter. So for example, this is the chemical structure of Zidua. And one of the primary ways that Zidua is attached to the soil is through interactions with organic matter, okay? Another example would be this ligand bonding process. And basically that's just a fancy way of saying that some of these elements that occur on the surface of these clays act like bridges and attach the herbicide molecule that way. So this is the chemical structure for glyphosate. So glyphosate is an example of a herbicide that is bound very rapidly and very tightly by ligand bonding. So no residual activity here. Another example of a herbicide that has no residual activity and is very rapidly and very tightly bound would be paraquat. So paraquat, the molecule itself has a positive charge and is very tightly or very rapidly attracted via electrostatic interaction. So that positive negative charge interaction to the negative charges on the surface of the soil. So those are just some of the mechanisms that cause herbicides to interact differently with the soil. And so you may say, Sarah, this is not super applied, but it is, because when you understand these characteristics of your soil, so do you have, for example, high organic matter? Do you have a particular type of clay? You can start to understand why herbicides behave the way they do and how you can best use them in your particular environment. Now, the last aspect here that I want to focus on is herbicide degradation in the soil. So this is really kind of the crux of the issue here. This is what we're going after. Because degradation is the process that determines how long these herbicides are going to be active. So there are really three types of processes that influence the rate of degradation in the soil. The first would be photodegradation. And so those are just processes that are associated with light. Not super common as a primary means of degradation, but some products are susceptible to photodegradation. Prowl, the yellow herbicides, the dinitroanilins would be an example of that. A second category here would be chemical interactions. And so these are really, when we think about herbicide degradation in the soil, really these are a function of soil pH. Okay, we think about products that are susceptible to this parameter, and we think a lot about maybe atrazine, which can have acid hydrolysis, so it's going to degrade faster at low pHs. And also the ALS inhibiting herbicides, the sulfonylureas and the imidazolinones, pH can affect how they degrade. So in particular, things like the sulfonylurea herbicides can have a longer residual activity in the soil when they're used in soils with higher pHs. So again, know your soils so that you can know what the label says so that you can choose the right rates or choose the right product. Sometimes these interactions with soil characteristics will eliminate a product from being used in your system. The third and most common cause of pesticide degradation is microbial degradation. And this is just a process where the organisms that live in the soil, so our bacteria, our fungi, all of the things that we're talking about when we talk about increasing soil health, okay, all of that, those microorganisms, they use the herbicides either as a primary source of energy, so just like we go to the salad bar, right, they're eating, or they're actually creating enzymes that just happen to be able to break down these herbicides. So this would be like, my family likes black olives on their pizza, guys. I don't. Sometimes I accidentally get a black olive in my pizza. So that would be kind of an example of co-metabolism in those bacteria and fungi breaking down herbicides, even though they're not intending to use them as an energy source. So let's look a little bit more deeply at microbial degradation. There are a few things that have a big influence on the rate of microbial degradation. One of those is sorption. So generally speaking, it needs to be maintained in the soil long enough for the microorganisms to break it down. So things that are really water soluble and leach quickly are not super susceptible to microbial degradation, but also if the key components of that molecule are sorbed and interacting with the soil, they're probably not available for the microorganisms to munch on. And so if something is really tightly sorbed, it's not going to break down super quickly either. Another characteristic would be previous applications. So this is something we think about a lot with atrazine and how it's a process called enhanced degradation. So if we've applied atrazine in the past, the microorganisms in that soil are adapted to using that as a food source or having that around, and so they can break it down faster. This is a more recent research example of a sulfonylurea herbicide and how it breaks down with soils with no history of application, which is represented by the solid line here, versus soils with a history of application, which is represented by the dashed line here, okay? So over 45 days here, they saw a more rapid decrease in the concentration of this herbicide in the soils that had a history of previous application. So this can affect how long we get weed control from our residual herbicides. So when we talk about degradation, really what we're interested in here is the inverse. We're really interested in persistence. How long is that herbicide going to stick around? So, herbicide persistence is just a fancy way of saying that it's the length of time that the herbicide is going to be active in the soil. We typically use a term called half-life to describe how this works. So basically a half-life is just how long it takes half of a concentration of a herbicide to be degraded or to disappear from the system. And so sometimes that's a nice, pretty straight line, but usually it's not. Usually that half-life actually depends on the starting concentration. So we use some mathematical models to figure out kind of what that looks like. And a lot of times we end up with kind of wonky curves like you see in this graph here on the right. So when we think about herbicide half-life and how that relates to herbicide rates of application, when herbicide rates of application are delineated on the labels, they're really looking for something that's between two different ranges here. The upper limit is going to be the minimum amount that we have to get adequate weed control for an extended period of time. Okay, we want to have enough herbicide in the soil so that we do get some extended weed control. However, we don't want to have so much herbicide that we cause unacceptable crop injury or carryover for too long or carryover. So that extended period of activity that actually ends up causing harm to crops in subsequent growing seasons. So there's a window of concentration here that we're shooting for to get some weed control but not have unacceptable crop injury or carryover. And so carryover is where I kind of want to hang out for the rest of this webinar. So carryover is just the term we use when we talk about concentrations of the herbicide that occur in the soil that have a negative impact on our crop for next year. This table is showing some of the herbicides that come up in conversation when we talk about carryover injuries. So here at the top, we have some ALS inhibiting herbicides in group 2. We've got our sulfonylureas like Classic and Glean, and then an imidazolinone herbicide in Pursuit. So these herbicides have the same target site in the plant, but structurally, those building blocks are a little bit different. And you can see that affects how they act in the soil. Classic and Glean have a little shorter half-life than Pursuit. Classic and Glean tend to be primarily broken down by hydrolysis, so a chemical reaction in the soil. The primary mechanism for degrading Pursuit is microbial activity. Moving down the list, we have a couple of group 5 herbicides here in atrazine and metribuzin, really fairly similar in terms of the possible ranges of their half-lives, and both primarily microbially degraded, although we mentioned before there is some hydrolysis at low pHs. The next group of herbicides we have on this list would be our group 14 products, our PPO inhibitors, things like Reflex and Authority. They have even longer half-lives, okay? Oddly enough, Reflex, one of the primary mechanisms of degradation listed for Reflex is photodegradation. So there's an example of one of those rare instances where microbial activity is not really one of the main mechanisms of degradation. However, the research suggests that microbial degradation is the primary mechanism of action for sulfentrazone and also for Callisto. Okay, so Callisto has a really short half-life here in the soil, but it is primarily broken down by microorganisms. So we want to talk about this list so that you can see that a lot of these herbicides are influenced by microbial degradation. And so the environment has a huge impact on the rate of microbial activity and the likelihood of the potential for carryover in future years. So this is yesterday's Drought Monitor. And let's just focus in. I'm a little partial here. I'm from Kansas. Let's take a look at Kansas. You can see much of the western portion of our state and the northern portion of our state has been impacted by drought. And we have, for the last few calendar months, do have a significant deficit in precipitation. And so one of the things we've been talking about this winter is that some of these products could potentially still be hanging around in the soil, and we potentially have an increased situation for herbicide carryover injury going into the 2021 growing season. Drought affects the potential for herbicide carryover because it affects the microbial activity, which translates to lower levels of breakdown of degradation, so longer persistence. So if we look at these graphs, they're set up here. The y-axis is just the amount of herbicide that is present in the soil, so the percent remaining. And then here on the x-axis, they're just looking at time. So they went out 56 days in these experiments. I know there are a lot of lines on these graphs, but we're going to make it simple. I want you to look at the lines here with these solid black circles. That is the line that represents isoxaflutal, or the active ingredient in balance. Okay, so here in dry soils, they had a significant decrease in the concentration here, somewhere between 7 and 14 days. Okay, that's where that curve really starts to go down on that graph. Now, if we hop over here to the wettest soil that they looked at, really what they've got here, their first reading already had a lower concentration, and they saw significant decreases in activity, even before 7 days. This is probably 2 or 3 days after application here. So you can see that in those moist soils where the microorganisms had plenty of water to be happy and active, this product balance was broken down much more rapidly. A second characteristic of the environment that can affect microbial activity is temperature. Okay, so these graphs here are looking at a sulfonylurea herbicide, and similar to the previous slide, they're just looking at what percent of the applied herbicide is left. Okay, they looked at this response in 2 different temperatures, so a cooler temperature and so 43 degrees Fahrenheit and 60 degrees Fahrenheit. But I'll say here at the outset that the 60 degrees Fahrenheit really isn't the ideal temperature for most soil microorganisms. We'd want to see another probably 20 degrees, 15 or 20 degrees added to that to hit about 75 or 80 when we really think about that peak temperature for activity for a lot of herbicides, or I'm sorry, a lot of microorganisms that break down herbicides. So in this case, what you can look at right away, well, first thing I want to point your attention, this green line here, so that is just showing soils that didn't have any microorganisms. So you can see that the microbial activity was really important for breaking down this particular herbicide. But you can see the differences in temperature just by looking down here at the length of the x-axis. So at the lower temperature, the 43-degree temperature, they had to carry this data collection out all the way. They went out to nearly 300 days. So, you know, they started leveling this line off somewhere here about 120, 180 days. Now come over here to the 60-degree data. Check it out. They only took data out to about 70 days. Okay. So this is just evidence here, guys, that this curve decreased much faster when the temperatures were more ideal for microbial activity. So if we have really cold winters or cold falls or cold springs and that soil stays cold for a longer period of time, we're more likely to have herbicide carryover. And then we've talked about soil pH. So these are some data looking at pursuit. And again here, these lines are just looking on the y-axis here at how much of the herbicide that was applied are they still detecting after a period of time, okay? And again, look at these solid black squares. That's the actual imidazopyr, that active ingredient in pursuit. The other lines are some of the byproducts that get formed as the microorganisms work on that imidazopyr molecule. So we've got a couple of different pHs here. We've got a pH of 5. So, you know, really lower than ideal for a lot of our cropping systems. And then a pH of 7. So that's getting on the higher side of where we might want to be. And then a pH of 7. So the thing I want you to notice here is how much more rapidly the line of the imidazopyr concentration decreases at pH 7 than it does at pH 5. Okay. So it breaks down faster at higher pHs than at low pHs. We've looked at some factors that influence the potential for carryover going into the 2021 growing season. We've talked about drought and looked at the fact that there are large areas of the country that have had much lower than normal precipitation in the last few weeks or months. We've talked about soil temperature, and you know, we can think about the fact that much of the country had very, very significant cold temperatures that will probably delay how fast the ground warms up here a little bit this spring. We've talked about soil pH. We've talked about soil organic matter. Okay, so these are all factors that affect how the herbicide is going to behave in the soil and how likely it is to carry over. So how do you, as a farmer or an advisor, address this? So point number 1, the label is the law. Always double check the labels. A lot of these residual herbicides are going to have tables within the label that specify for given soil conditions, such as texture, organic matter, pH, maybe by soil series, what is the best rate or what is the appropriate rate, or even if that product can be used. So use the correct rate for the soil and the environment in which you are working. That's step number 1. Step number 2, all of these herbicide labels will have rotation intervals listed on there. So how soon can you come back with a different crop? Respect those rotation intervals. They are there to protect, really they're there to protect the industry, but they're also there to protect you as a farmer, because you don't want to have that unacceptable injury going into next year. So respect those rotation intervals. Something else to think about is to be aware of varietal differences in sensitivity. So this could be something like being aware of the fact that, for example, clear field crops can tolerate residues of sulfonylurea herbicides. So here in Kansas, we talk a lot about using those sunflower or soybean varieties that are not sensitive to some of our residual herbicides that we use in wheat. So that can be important. Another example of varietal differences would be things like maybe soybean or wheat differential responses to metribuzin. So just be aware of that and double check with your seed source if you have any doubts. And then the last item on the list here requires a little bit more effort, but it's to conduct a bioassay. If you're really just not sure, if you have concerns and don't know how to predict the likelihood of having problems from carryover, you can conduct a bioassay. And basically this involves going out and collecting a soil sample from your field of interest. So you're going to want to make sure, maybe you need to look at a couple areas, maybe, think about the headlands where we might have overlap depending on the sprayer technology that you're using versus maybe a low spot in the field versus a high spot in the field. So you want to make sure that you're representing some of these areas. You want to make sure that you're collecting soil from the depth in which you'll be planting your crop. So, think about maybe a couple of inches there. And then you also need to collect a non-treated soil sample from a nearby area. So maybe this is, a field edge that's going to have a similar soil, just not treated with herbicide. So collect both of those soils. And you want to, very quickly after you collect them, you want to do these next steps, because as these soils dry out, if they're exposed, just the biology that happens in those soils will change the results. So you want to put those soils in pots. You want to grab some of your crop seeds and seed those in there and then grow those, right? Put them in a place where those seeds are going to grow. Maybe that's a sunny windowsill in your shop or your house, but just put them in a place where they're going to be able to grow. And then after a couple of weeks, you'll be able to compare the seedlings that emerge in your treated soil and your untreated soil to see if you have herbicide injury symptoms. Obviously, if you have herbicide injury symptoms, that tells you that you're pretty likely to have carryover issues in your field, and it's a lot better to have found out in that pot than it is to have found out in your field. So with that, I thank you all for your time listening to this webinar, and if you have any questions or if I can be of any other assistance, please feel free to reach out to me using the information that's presented on this slide. Thanks.